The Larson Optic Survey Telescope, or LSST, is a new telescope that will use these advances in technology to allow us to get a better and clearer image of the universe. I'm Bowden, and I'm working under Professor Andy Howell at Larson Observatory. So the Larson Optic Survey Telescope definitely lives up to the large part of its name. A larger telescope allows us to see further. You can see here that we have a model of what the telescope would look like with a person down here, as well as a picture of one of the mirrors of the telescope next to some people for scale. So you can see it is quite large. However, there are many large telescopes in the world, and that's not what makes this telescope special. What makes this telescope special is that it will be able to monitor changes in the sky in very faint objects. The telescope is set to be completed in 2022, and it will begin a 10-year pre-programmed survey, which means they have to decide the observing strategy in advance, meaning where the telescope will look at a certain time in the night. The current proposed observing strategy can be represented by this map. Just like we can take a globe and project it onto a 2D surface, we can do the same thing with the map of the sky. So the telescope is in the southern hemisphere, which is why the northern hemisphere up here is all gray, can't see the sky from the northern hemisphere. The main region of the telescope survey is this wide, fast, deep survey region, all of this blue. This is the region where the telescope will spend 90% of its time looking. And the areas that are different colored are areas that the telescope will visit more or less times. For example, these areas that are slightly darker blue right here, these are called deep drilling fields, and they're places where the telescope will look more often than average. The observing strategy has a big impact on what we are able to observe. So different areas of research are more compatible with different observing strategies. So they want to be able to balance all of the different science goals that people are trying to accomplish using this telescope by coming up with an observing strategy that can meet all of these needs. I want to figure out what observing strategy is the best for observing supernovae by comparing different observing strategies and seeing if there are small changes that can be made that would greatly increase our ability to observe supernovae. Supernovae are events that take place over a very short amount of time, and we measure their brightness over time. So the Larson Optic Survey Telescope, with its ability to monitor changes in time, has the potential to observe a large number of supernovae. So what is a supernova? We begin with a massive star, and much larger than our sun. And with this star, it needs to burn fuel in its core in order to produce the energy to keep it from collapsing in on itself. However, towards the end of its life, it starts to run out of fuel and it becomes unstable and then can explode in a supernova. I have here a little video of this is a simulation of what a supernova might look like. You can see here, it's still relatively stable, and then going to go. Boom. And you can see its brightness is increasing over time after the explosion. So how do we observe supernova? The telescope will take images of the sky, and it'll take an image of a distant galaxy like this one. We can see the supernova down here in the corner right here. This supernova is incredibly bright. It can be as bright as all the rest of the stars in this galaxy combined. If we have a series of images like this one, we can figure out what the brightness over time looks like and use that to create a light curve like this one here. Notice on the y-axis we have magnitude. This is inversely proportional to brightness. So as we go up here, even though the magnitude numbers are getting smaller, this is increasing brightness going up the y-axis. If we look at the time after the initial explosion, we see that there is an increase in brightness until we get to the peak a little after 10 days. Then over the next several weeks, the supernova will fade. So this is a relatively short event. From the light curve, we can figure out many of the physical properties of the supernova. We're especially focused on what the magnitude of the peak is, as that contains a lot of information about physical properties of the supernova. What I want to do is determine LSST's ability to observe supernova. What I do is I start with a template of a supernova, and what this is we have a good idea of what the brightness over time looks like for some types of supernova. And we can use this idea of what the brightness over time looks like to construct a model of what we think the supernova should look like. And then we take this template and we place it at a certain spot in the sky on a certain night during the survey. And we use a simulation created by LSST to simulate their observing strategy. And using this, we can see when the telescope would look at the right spot in the sky to see this supernova. Then, using what the telescope would see, we can compare that to our template. Now, how do we use light curves to do this? We start with a template like the one I showed earlier, and then we run it through LSST simulation. And what we get back are these points here. If you see here, we have the telescope sees it around day 5, and then it will look away, look at some other spots in the sky for a while, and then look back around day 15, and so on. Now this is a relatively well-sampled spot in the sky, meaning that the telescope observed the supernova many times. However, we found that for many spots in the sky and times during the survey, that we had 0 or only a few observations during the course of the supernova. Our result was that in the main survey region for the current proposed observing strategy, only about 1% of supernova had at least 4 points in the first 30 days. For those 1% that we did consider having sufficient points, we fit a polynomial to those first 30 days. We don't care so much about this tail of the supernova because what we're focused on right now is figuring out where the peak happened. So using this is actually a quadratic. Using this quadratic, we can compare it to our original light curve, and by comparing where the peak occurred, on what day, and what magnitude. So you see here, we have a histogram comparing the actual peak versus the peak that we found with our polynomial. So this is actual magnitude minus the guessed magnitude, the magnitude from our polynomial. Ideally, this would be a very thin bell curve, and that is almost what this looks like, as that would tell us that our guesses were almost always very accurate. However, we do see a few differences out here around 0.3 and 0.4 magnitudes. Depending on the type of research you're doing, this would be accurate enough, or you might need to make the restrictions tighter on what we consider to be a sufficiently sampled supernova. Also, we measured the difference of peak day, so the actual day minus the guessed day. And you see here it's slightly more spread out than the peak magnitude, and we have some differences around 4 days, which leads us to the same conclusions as the first graph. Because we found that you can only observe about 1% of the supernovae sufficiently in the main survey region, we would like to compare this with different observing strategies and see if there's any small changes that could greatly improve our ability to observe supernovae. Some other things that we would like to look at is other properties of the light curve, such as the day of the explosion and the shape of this tail, as these also contain important information about the properties of the supernova that we would like to be able to retrieve from the data we have from LSST. Another thing that we would like to look at are different areas of the sky and see if any areas of the sky are better for observing supernovae or worse, given a certain observing strategy. For example, those deep drilling fields that I mentioned earlier, the areas in the sky where we observe more often, we found that 40% of the supernova in those areas are considered sufficiently observed compared to the 1% in the main survey region. I'd like to acknowledge my mentor, Andy Howell, as well as postdocs that I work with, EUREKA and Curtis McCulley, for all of their guidance and assistance, as well as the undergrad that I worked with, Megan Newsom, and the EUREKA program for funding me. Thank you.